Okay, chapter 13 is problems about temperature. So we need to convert between different temperatures. On January 22nd, 1943, the temperature in Spearfish, South Dakota rose from -4 degrees F to 45 degrees F. In 2 minutes, what was the temperature change in degrees C? So we want to go from temperature in Fahrenheit to temperature in Celsius. The temperature in Celsius is equal to the temperature in Fahrenheit minus 32 degrees and then times 5/9. So -4 degrees F is equal to 5/9 -4 minus 32. So it's -20 degrees C plus 45 degrees F. In C, it's 5/9 45 minus 32. And I get 7.22 degrees C. So the temperature change is temperature final, 7.22 minus temperature initial minus 20. I get 27.22 degrees C. All right, part 2. Now I've got temperature change in Fahrenheit. Sorry, in Celsius, I need to put into Fahrenheit. This should be Celsius there. Okay, so I've got my initial temperature was 6.7 degrees C. So I need to go to F. So my temperature in Fahrenheit is 9/5 the temperature in Celsius plus 32. So that's going to be 9/5 of 6.7 plus 32. And I get 44.1 degrees F. And the second one is -48.9 degrees C. That's pretty cold. The temperature in Fahrenheit is 9/5 times -48.9 plus 32. I get -56.0 degrees Fahrenheit. So the delta T is final minus initial. So -56 minus 44.1. I get temperature change of more than 100 degrees Fahrenheit. You need to be able to do basic temperature conversions from C to F and from F to C. All right, second problem involves linear expansion. We've got a bridge that's 1,410 meters long. That's the original length. Temperature changes from -5C to 18C, and we want to know the change in length. So the change in length is equal to alpha times L0 times delta T. That's our equation. Alpha is 1.2 times 10 to the -5 per degree Kelvin. Now, per degree Kelvin is the same as per degree C because one step in C is the same as one step in Kelvin. Okay, so I can just substitute that in directly. My original length is 1,410 meters. And my change in temperature is T final minus T initial. So that's 18 minus -5. It's going to be a change of 23 degrees. And I get 0.389 meters. So that's about 38.9 centimeters. Okay, so it's changed in length by over a foot. That's quite a considerable change in length. All right, let's do another thermal expansion problem, but now with volume expansion. So I've got a drinking glass that's filled to the brim with water, 268.4 milliliters of water, at 5 degrees C and placed in the sun. If the temperature of the water rises to 32 degrees C, how much of water will spill out of the glass? And we're going to assume that the glass doesn't expand. Okay, of course, the glass will expand slightly, but because that expansion is so much less than for the water, we're just going to ignore it. Our original volume is 268.4 milliliters, and that's 268.4 cubic centimeters. 1 milliliter is 1 cubic centimeter. And as long as I want my answer still in milliliters or cubic centimeters, I don't need to convert that into cubic meters. But if I had to, I could do it. So I could do 268.4, and my conversion is I got to cube my conversion. I want to go from centimeters to meters, 100 centimeters in 1 meter. So that's 268.4 times 10 to the minus 6 cubic meters. Okay, so our equation is delta V. It's the change in volume of the water. That's how much is going to spill out because the glass is filled as far as it'll go, is equal to beta, the expansion coefficient, which we're given, times the original volume times delta T. So it's just the same as what we did on the previous one. 207 times 10 to the minus 6. Again, per degree Kelvin and per degree C are the same. Our original volume, I'm just going to leave as 268.4 milliliters, and that'll give me my answer in milliliters. And my change in temperature, I'm going from 5 degrees to 32. So 32 minus 5 is my delta T. And I get 1.50 milliliters. Okay, so 1.5 cubic centimeters will overflow from the glass. Next thing is ideal gas law. I've got helium gas that has a volume of 2.60 liters and a pressure of 0.180 atmosphere at a temperature of 41 degrees C, is warmed until both the pressure and the volume are doubled. I want to know what's the final temperature. All right, so ideal gas law, PV equals nRT. Okay, so P1 is 0.180 atmosphere. V1 is equal to 2.60 liters. And T1 is 41.0 degrees C. In our second position, our pressure is doubled, so I've got 0.36 atmosphere. I've got a volume of 5.20 liters. And my temperature is what I'm trying to find. So if my amount of material stays the same, then PV over T should be constant. So P1 V1 over T1 is equal to P2 V2 over T2. All right, now I've got my units as strange numbers. I've got atmosphere and liters and C. I should have pascals, cubic meters, and Kelvin. Which is important? Well, turning this temperature into Kelvin is the most important thing. Conversion factors on these sides will cancel out because they're multiplicative, but for temperature, it's additive. Okay, so T1 is equal to 41 degrees C plus 273.15 to give me the temperature in Kelvin. So I get 314.15 Kelvin. All right, so I want to find T2. So rearrange it. T2 is equal to P2 V2 T1 over P1 V1. And so I get 0.36 times 5.2 times 314.15 divided by P1 V1, 0.18 and 2.6. And so I get my temperature is 1256.6 Kelvin. So that's a very large temperature. All right, what if I did it where I actually did my question in 2 steps? First I find how many moles of gas I have, and then use that to find T2. All right, so then I would find N, the number of moles, is P1 V1 over R times T1. Now I have to put my pressure and my volume into the correct units. Okay, so pressure, P1 is, I'll do it up here, 0.180 atmosphere times 101.3 times 10 to the 3 pascals per atmosphere. And so that gives us a pressure of 18,234 pascals. How about the volume? I've got 2.60 liters. I need to convert that into cubic meters. There's 1,000 liters in 1 cubic meter. Okay, so this is 2.6 times 10 to the negative 3 cubic meters. Alright, so now I've got those in the standard units, put them in. I've got P, 18,234 pascals, times the volume, 2.6 times 10 to the negative 3 cubic meters, divided by R, the ideal gas constant, 8.31, and the temperature, original temperature is 314.15 Kelvin, and I get 0.0182 moles. So that's how many moles I have. And now to get T2, I'll use T2 is P2V2 over NR. And now I need my P2 in pascals. So P2 in pascals is going to be twice this, because I got twice the pressure, so 36,468. And I've got twice the volume, so 5.2 times 10 to the minus 3 cubic meters. So I've got 36,468 times 5.2 times 10 to the minus 3 over n, 0.0182, divided by 8.31, the ideal gas constant, and I get the same answer. Okay, it's slightly different because of rounding errors. I get 1254 Kelvin. If I'd kept enough significant figures, I would have got exactly the same answer doing it the two different ways. All right, part B, how many grams of helium are there? Well, now I know I have 0.0182 moles, and I've got 4 grams per mole. So just multiply those two, and I get 0.0728 grams of helium. Question 5. I've got another ideal gas law question. I've got gas at 20 degrees C, so T1 is 20 degrees C, or 293.15 Kelvin. The pressure is 155 kilopascals, so times 10 to the 3 pascals. T2 is equal to 70 degrees C, which is 343.15 Kelvin. And I want to know what's the pressure. Okay, well, what happens to the volume? Well, volume, the gas is held inside the bulb, so the volume is the same in both cases. How many moles of gas do I have? It's going to be the same in both cases. All right, so I've got P1 V1 equals nRT1, P2 V2 equals nRT2, and I have the T's, and I have one of the P's. I want P2. So what can I do? Well, what if I divide these equations by each other? So I do P2 V2 equals nRT2 and divide that by P1 V1 equals nRT1. Okay, so P2 V2 over P1 V1 equals nRT2 over nRT1. Now V2 and V1 are the same, so that cancels out. N and R are the same. So basically the ratio of the pressures is equal to the ratio of the temperatures. And remember, we said that was one of the laws that was originally discovered. If you keep the volume the same, then the pressure depends linearly on the temperature. So P2 is just equal to the ratio of the two temperatures in Kelvin times pressure 1. So it's going to be 343.15 over 293.15 times 155 kilopascals, and I get 181.4 kilopascals as my pressure. You notice that if I had done this in Celsius instead of Kelvin, I would have had 70 over 20, so a factor of 3.5 here, and I would have had a much different answer for my pressure. You have to convert the temperature to Kelvin to get the correct answer. Okay, final question. This is related to the speed and kinetic energy of a particle. What's the temperature of an ideal gas whose molecules have an average translational kinetic energy of 3.2 times 10 to the negative 20 joules? So we've got two equations that we learned in kinetic theory of gases. One is that the kinetic energy is equal to 3/2 times Boltzmann's constant times the temperature. And the other one we had is that the RMS speed is 3k Boltzmann's constant T over m. That's just setting this equal to 1/2 mv squared. So we're going to use this equation. I've got the kinetic energy. I've got K. I want to know what's T. So T is equal to 2 times the kinetic energy over 3 times Boltzmann's constant. Okay, so 2 kinetic energy is 3.20 times 10 to the negative 20 joules divided by 3 times Boltzmann's constant. And Boltzmann's constant is 1.38 times 10 to the negative 23. And I get 1,545.9, and that will be in Kelvin. Okay, so it's quite a high temperature. All right, second question asks us for RMS speed given the temperature and the mass. Okay, so VRMS is just the first equation, 3 times Boltzmann's constant times T over m. I need to put my temperature in Kelvin. So my temperature is 27 plus 273.15, 300.15 Kelvin. Okay, so I've got 3 times Boltzmann's constant, 1.38 times 10 to the negative 23, times 300.15 divided by the mass, 1.38 times 10 to the negative 17. Take the square root, and I get 300 meters per second. So the gas molecules move pretty fast.